Hello, everyone. Thanks a lot for the opportunity to speak here. This is supposed to be a fun talk. It's going to remind you of your old college days. It's about teaching computer science, and it will have some of that content and also some new things that we are developing. It's about a system that's called Selfie, a sandbox for principal systems engineering, and I will explain why we came up with this name, and that it has nothing to do with the selfie that you take with your phone. There's also nice pictures in the talk taken in Australia and Austria. In case you don't like the talk, you still have to have some nice picture to look at. Okay, this is joint work with many people, mostly students at this point, but also some colleagues outside of Salzburg, where I teach. This work is also inspired by big names in the field, and you will see that actually when you look at the design of the system, that there is strong influence from these people. Armin Bierer, an expert on SAT solvers, is actually the person who told me about this event here and encouraged me to come. He attended last year. So this talk is about teaching computer science from first principles, actually. And the idea and the motivation came up in 2014 when I was invited to teach a computer science class to civil engineers at Berkeley. And that was an experience for me. When I started teaching that class, I prepared everything. I realized within a week that I completely had to redesign the class. I completely overestimated the background of these students. It turned out that they were all coding every day. Actually, they were investing more time in coding than anything else, the actual topic of their studies. Okay. And this is actually true for many other fields as well. So this talk is not just about teaching computer science to students in computer science, but it's also trying to actually reach out to broader audiences, which I learned back then. And the result we have today is the Selfie system that actually was motivated by that experience. These students, they actually told me, I asked them, how do you actually program without really understanding what you're doing? And they said, Stack Overflow. and Google. That's it. So they ask a question, they find an answer, they copy the code, some code snippets, and they put it together and build actually enormously complicated systems, civil engineers, right? And I'm sure it's true for many other fields. This talk is not just about teaching, it's also about research, because interestingly, I was afraid actually starting to invest too much time into teaching because, you know, you have to write your papers, write your grant proposals, etc. But it actually turns out to be an extremely interesting experience when you are forced to actually sit down and really come back to the absolute basics so you can actually teach this stuff to people who have no clue. And what comes out of that is actually not just a teaching tool, but also a new platform for research. So the main question that I'm asking here with the system is, how do you create semantics on a machine? How do you create the meaning of notation like this, of programming languages, of machine code, assembly, etc.? And it turns out that there is a lot of, in the construction of this, of semantics, of formalism, there's a lot of self-referentiality. And this is actually this is part of the key challenge for people to actually understand how to resolve this. And the system, our system that we created here, tries to actually do that. So we are teaching, with this thing, we are teaching the construction of the semantics of formalism, such as programming languages and machine code. And we do this through different means. First of all, compilation. So there's a compiler in the system. Yeah? And I'm teaching in a class how this works, etc. There's also an interpreter. It's in fact an emulator that's based on an interpreter of machine code. It's another way of showing how to construct semantics. But there's also virtualization in the system, which is extremely important today to explain to students and also civil engineers how the cloud actually fundamentally works. And they don't understand that. But it also turns out, and this is actually our ongoing work, that verification is a particularly interesting, provides particularly interesting perspective on the problem of creating semantics. Yeah? So the system is the following. Selfie is actually implemented in a single file of C code, 7,000 lines of code, and the file is called selfie.c. You get it on GitHub, and you can compile it and run it. It implements the following pieces. It implements a self-compiling compiler called *C that compiles a tiny subset of C called C* to a tiny subset of MIPS32 called MIPSTER. Okay? And C*, I'll talk about the language. This is actually a very important part of the project, is a tiny subset, and there's also, so I have an example about that. There's also a self-executing emulator part of this code called MIPSTER that executes this code, including itself, of course, because it's part of the code, right? When compiled with this compiler. You will see in just a few minutes why this makes sense. Okay. There's also a hypervisor called Hipster in there. I know I have something going on with names here, but this is how students listen and remember. Okay. Hipster virtualizes the machine created by the emulator. Okay. And it does this in such a way that it can host all of Selfie, including itself, any number of times until time and space runs out. There's a library, libc*, part of this because the system is fully self-contained. Right? There's no include, there's no import, there's no library other than its own library. Everything is implemented in this 7,000 lines of code. Okay? And we study all of it. And now I'm reaching out to verification. We started actually implementing verification technology into it. Our first experimental SAT solver is super primitive, and that's why we call it baby SAT, but it actually does work. And there's more on that later. There's also a linker in memory. There's a disassembler with source code line numbers referring back to where the stuff comes from, where the code comes from. There's a debugger. There's a profiler in this code. All of that in 7,000 lines of code. That's what you can do, actually. And there's also RISC-V support. That's in a separate branch, and you can check that out. It actually generates RISC-V code in ELF binaries that you can execute on the official toolchain. This thing is already Selfie is already a little famous. It already got quite a bit of discussion on Hacker News. I was very pleased to see that. There's a website. There's a book that I started writing and never finish, and then there's lots of code, etc. Okay? There's also, I'm going to talk about this soon at Splash, because Selfie actually not just helped me, or does not just help me teach students, but it also helped me derive the very basics that I believe need to be taught to broader audiences so they understand computer science more fundamentally. There's, of course, lots of other efforts in the world that are trying to do that, and so I just throw them out here. So here's code written in C*. This is the famous ASCII to integer routine that you might remember from your studies. This actually implements the semantics of decimal numbers, right? It takes a string and then computes the numerical value represented by this string. So you see that actually in this line, this is the key. And you can see here that this is a base 10 representation that we are using and compute this in this recurrence relation. Beautiful. And you can actually see here most of the C* features. So the language is actually just assignment, while, if, return, and procedure invocation. That's it. And in particular, there's no data types, right? So I'm going to see how the programming language community reacts to this. There's only int, signed integer, and pointer to signed integer. Actually, and a dereferencing operator that allows me to access any of the dynamically allocated memory, or any memory, actually. And that's why we call it C*. Now, this is very important. This was actually the breakthrough idea to just kick out all the data structures, right? Very important aspect of the whole project. And then in the classes, we come back to it and implement all the things again with the students. You can see this here, that we're actually using this stuff in the code, and in particular, this actually gives rise to two different kinds of arithmetics that most students don't know about, integer and pointer, of course. There's character literals and string literals purely for readability. I didn't want them in there, but I had to put them in there because otherwise it's just a mess. And there's more here, or actually less, no bitwise operators and no Boolean operators. No bitwise operators is a performance problem, and I'll teach the students using the profiler why this is the case. No Boolean operators is not a big deal. What's important also is that this is what we depend on. 5 calls that we need, and GCC, for example, when you bootstrap this thing, actually allows you, it doesn't complain about this. It actually just includes the wrapper code for this, and you're done. You don't have to do any linking here. We need exit, of course. We need malloc. Nobody needs free. We need open. Simplicity, okay? Absolutely, you know, the simplest thing you can do. Open, read, write, nobody needs close, okay? Anything you want in addition, you implement yourself. That's what I tell the students. So if you want structs or anything else, you need to implement them. And this is actually a very interesting experience for them. Okay, so what I'm going to do now is I'm going to show you how to bootstrap this thing and actually use it, okay? So we are bootstrapping selfie.c on our x86 machine, let's say, using a standard C compiler, okay? And we'll get this binary called selfie, okay? Now, the usage is as follows. It's a little bit non-standard here, but I have to say a few words about this. So first of all, there is this option for compiling code, and you can actually provide as many files as you want, and they are going to be linked in memory together, okay? The important thing here is that the compiler compiles the code and stores it in memory, but it doesn't emit any code. You actually have to specifically say, I want that code in this binary, using this option -O. I can also generate assembly code same way. I also have a loader here that actually takes the binary back from a file and loads it into memory, okay? And then the interesting thing starts here. This is an option -M starts a MIPS instance with this much memory size, like 2 megabytes of physical memory, and then takes the code that is in memory and executes it. It boots the machine, a MIPS machine, and executes it. I can also do this in debugger mode, and in particular, I can also run the hypervisor version of it, which of course only would work if I'm already running on a MIPS machine, right? Otherwise, the hypervisor doesn't work. Okay, and we'll see that now in these examples. So the first thing I'm going to show you is compiling selfie with the selfie executable. This takes seconds on our machine and works like this, okay? Actually, but it doesn't emit any code, right? So it compiled it, and it gives me a nice statistics of what's in the source code. You can see we have 7,000 lines of code, but we have almost 1,000 comments in there. And so the code is actually meant to be read. Okay, so it takes seconds. This is important to know. Next is, like all compiler people, what they want to do is they compile now this thing with selfie, create an executable, but then want to execute that executable to compile itself again. Okay, so this is what we are going to do in a single invocation of the system. Okay, so it works like this. It compiles selfie, and then I create an instance of the machine that will now execute what I just compiled, and it will receive the rest of the argument list as the argument of this particular code, right? So I'm starting a MIPS instance here with 2 megabytes of memory, and then it will actually now execute the code that I just compiled before, but compile selfie again, right? Now I'm going to see a little bit more data here on how much memory got actually allocated with malloc 1.05 megabytes, and the underlying machine actually tells me how much of that memory was mapped. So it's actually more because of the binary that it had to load. This takes 6 minutes, because now I'm executing the MIPS code on my emulator to compile the whole thing again. Yeah? So this is slow, of course, right? Because the compiler is not optimizing, the emulator is slow, etc. But it doesn't matter here. Now, what people want to actually do when they are crazy about compilers is that they want to check what's called the fixed point, right? Is the first binary that I generated the same as the second binary, right? And it is, of course. And I can actually generate it on the fly using these options here, -o, selfie1.m in one file, and the other one, selfie2.m in another file. And then when you run when you run a diff on this, it's going to be identical. So now we have seen most of the system, but now we are getting away from compilers into operating systems. Okay, and what you can do with this is, I use this example here. You can actually teach students how to enhance the system and construct an operating system kernel in a 1-week homework assignment that can run n processes fully isolated from each other. How do you do this in a 1-week homework assignment without getting killed by the students? So what we do is we can run all this in a self-referential way. But in particular, what we can do is we can run the emulator on the emulator. So let's suppose we have one instance here and we run another instance on top of it, right? So for me, this here, this border between the two emulators is actually the machine now. Okay, so I consider that is my hardware, the whole thing. Right? And this is my operating system, actually. And in this case, my operating system here is executing code, one process, in full isolation from the machine, obviously. Yeah? So how do I run two processes in full isolation from the machine? And I completely don't care about performance whatsoever. Just the logic of what an operating system actually does, right? So I'll do this. And this is what the students can do in 1 week. They can have 2 instances of the same emulator, and then it just switches, let's say, after each instruction to the other emulator and executes it, right? From the perspective of the code that runs on these 2 different emulators, this is running concurrently on the same machine. Yeah? This is what an operating system logically actually does. But the big problem, of course, is the exponential blow up in complexity as you stack emulators on top of each other, right? With each emulator, you get a hit in performance, of course. So what does that mean? Let's suppose we'll do compile Selfie with Selfie, then again, and then again. Okay, so this is the invocation. Selfie, compilation, first machine, compilation again, another machine, compilation again. 24 hours rather than 6 minutes, okay? Of course. Now we have to, so in the end, what I'm teaching here is that operating systems are logically interpreters, right? But now how do we get performance back? And that's why they are complicated, and that's why it's so hard to teach them. In Selfie, it is very easy to do now, because I have this hypervisor that I throw in here, which of course has this nice thing of taking the code that it's supposed to execute, but it hands it down to the emulator, to the machine on which it runs to execute it. But it is supposed to do this functionally equivalent to the emulator, of course. Okay? And you can do this in Selfie just using a different option here, -y, at this level. And your performance comes back to, in this case, 12 minutes. 2 times 6 minutes. And that's essentially the performance you have when you run the code on one instance of the emulator. Okay? All right, so this is what you can do right now. And now I just want to use a few minutes and tell you what we are working on right now and want to work on in the future. So we are trying to take the bridge over to verification, in fact, to a more mathematical view on the system. And ongoing work is on integrating, in fact, a SAT and SMT solver into the system. So we are implementing it in C* in Selfie. And we have actually done so already with microsat, which is one of the state-of-the-art SAT solvers, and want to do this with Boolector, or at least some part of it. We are also working on a symbolic execution engine inspired by CLI and Sage, and maybe inductive theory improving a la ACL2. Microsat, the first result from this effort that we only recently started is that microsat, this state-of-the-art small SAT solver, when you port it to C star, it's just as fast as in C, right? Never mind structs, arrays, Boolean operators. They even use goto. We kicked this all out, replaced it by totally inefficient stuff, and then the GCC compiler with O3 just gets you the same performance. So it doesn't need any of this to actually figure this out. I think this is a great success of static analysis. Okay, we are also working on support of ELF binaries for our MIPS code that we are currently generating, x86 support, and, well, ARM support. I was told there's ARM people here. Maybe they're interested in that. Maybe. And if you don't believe that there's even a SAT solver in this 7,000 lines of code, there is, and you can run it on DMAX standard format problems, but it won't terminate on anything bigger than a few variables, of course. Okay, another nice picture from Austria. What is now the absolute simplest way of proving non-trivial properties of Selfie using Selfie, and what are these properties? Okay, so this is what we are working on. And I just want to give you one example very quickly. So suppose you have this emulator, right? This emulator is simple to implement because it runs on unshared program context, yeah? It's very simple to do. However, a hypervisor runs on shared machine context, right? It runs on a machine and needs to share it with the platform that it creates, right? And this, of course, makes it all difficult. The interesting proof obligation is, though, is the machine context created by the hypervisor equivalent, bit equivalent to the machine context created by the emulator? If you can show that, then you have actually you've gained some knowledge because the emulator is simpler. And we have actually worked towards this. We have introduced something called Mixter that is able to actually take code and execute 1,000 instructions using emulation and then change its mind and use a hypervisor to actually have the machine on which it runs execute the code and then go back and forth. And what we ultimately want to do is execute both in lockstep and then always compare that they're doing the same thing, and eventually through that prove that the system, that the hypervisor in particular, the context switching and spatial isolation to virtual memory actually is correct. Thanks a lot. And if you need a reason to come to Salzburg next year, you find that one. Thanks a lot.